Now the radiance is the light coming up off the reflected surface. So we'll just write this as E of the irradiance of the surface in some particular direction. The L is, I don't know why I guess we use L for radiance sometimes because it's actually the lightness of what you're going to be seeing. That's the radiance from the surface in some particular direction going out. And the BRDF, the bidirectional reflectance distribution function, is just the ratio of those two things, right? So it's the percentage of the light reflected as a function of the light coming in. Okay. A couple things about it is that obviously you can't reflect more light than came in, so that ratio is going to be less than 1. Now you might get a very bright spot in some direction if it were to integrate over all these different lights, but from one particular direction, the most I can do is send back all the light. I can't manufacture light. This is a passive system here. There are a couple of cool little properties of the BRDF. One, named Helmholtz after the guy Helmholtz. Basically, light doesn't know which way is up. Or another way of saying it is, it's a reciprocity. That is, that if the light source is coming this way and the camera is going that way, and I swap the camera and the light source, I get the same reflectance function, right? So it doesn't matter whether the light comes in this way and goes out that way, or comes in this way and goes out that way. There is no light diode for the nerds among us, all right? There probably are, you probably could build active light diodes, but for normal properties, we don't get that. For our purposes, there's another important property, which is referred to as rotational symmetry. And the way of thinking about that is, if I rotate the surface about the normal, nothing's going to change, all right? And what that essentially means is that I only have to worry about the little tangent plane right at the point that I'm looking. And so the only thing that matters is the relative direction between these, not just in terms of, here I want to talk about the amount around the angle. So the absolute angle doesn't matter, just the relative distance between them. And that's written like this. The absolute angle in terms of the tilt still matters. Okay, and we'll show you that in just a minute. But the rotation around is only relative around the normal. Bidirectional reflection distribution functions for real objects can be incredibly complicated. Here's a sort of little panoply of different types of reflectance functions. We're not going to talk any more about those. If you want to take a computer graphics course and learn how to render hair or it's just one down here, by the way, I think that's a peacock feather. That's actually not dye, but it's refractive. So bird feathers actually are not painted, if you will, but they refract the light through the material that's in it. It's a very complicated BRDF. We're not going to talk any more about that because we're going to talk about two specific reflectance functions that are special cases of BRDFs, and that you can combine them to sort of make most normal types of objects. And namely, we're going to talk about what's called diffuse or matte reflection plus specular reflection. Let's talk about reflection models. Here we have our surface, okay, and we have our incident light, and it's coming in. And it's coming in some particular direction, and this will be some theta I, which is going to be the tilt off of the surface normal. The first physical process I want to talk about is referred to as sort of body reflection. And what happens is the light comes in and it sort of scatters around at the top part of the surface, and then it comes out in lots of different directions. And therefore, it's impacted by the stuff that's in the surface, all right? And that's referred to as diffuse or body reflection, okay? And it tends to have what's referred to as a matte appearance and some sort of what's referred to as non-homogeneous sort of particulate matter have that kind of reflection. So this example here is this clay pot. If you think of this clay pot and you look at it, in some sense there's no shininess to it at all, right? It's purely matte. It's purely diffuse. And in particular, we'll talk later, no matter what direction you look at it, it seems to be approximately the same brightness. It turns out it's actually pretty hard to make purely matte surfaces. Like if you take matte spray paint and you spray something, even then there's sort of a certain amount of shininess to it, which we'll get to in a minute. But the general model that we're looking at of body reflection is the light comes in, is scattered about in the medium of the surface, and then goes out in a variety of directions. So that's the body or diffuse reflection model. So what else can happen to the light? Well, the other thing that can happen to the light is referred to as a specular reflection. Okay? So a specular reflection, just like you think, some of the light before we saw it penetrates down, etc., but some of the light doesn't. It just bounces straight back up. Okay? And that's referred to as surface reflection. And surface reflection is a specular reflection, and it's responsible for sort of the glossy highlights that you see on shiny surfaces, and in metals in particular. So here's a picture of a variety of things. This one, by the way, is a fake picture. That's to show you the highlights. But for example, shiny metal things, this metal pot. Here's an interesting one, right? Here's a can that clearly has stuff painted on it, right? So that's affecting the light coming in. It scatters around and bounces out. But you see also that there's this stripe here, right? Well, that stripe is the specular component of what's there. By the way, if you want to study more about specular things, the reason it works in metals, it has to do with the way the light interacts with the electrons that are in the surface. And that's part of what, makes metals metals, or these free electrons. Go take a look at your material science stuff. But those sort of atomic physical properties have an impact on how light behaves when it hits the surface. All right? And that's your specular reflection. And the general overall view of the universe is that the image intensity can be thought of as a combination of the body reflection plus the surface reflection. Okay? And as a reasonable model for what's going on, we can sort of model most surfaces as having a certain component of body or matte reflection plus specular reflection. Let's talk about now a specific mathematical model of body reflection. Remember before we said it comes in, bounces around a little bit, and then scatters out. Okay? So the model we're going to talk about is called Lambertian model, or it's Lambertian BRDF, but we'll just think of it as being Lambertian, all right? And we're only going to talk about the body reflection part. And Lambert's law, Lambert being the guy who did this, the sort of folksy way of thinking about it is that no matter how I look at it, no matter what direction of reflectance that I have, it looks to be the same brightness. That is, the only thing that's going to impact this is the incident component of the light. Not notionally, the more perpendicular the surface is to the light source, remember the radiance and irradiance thing, right? It gets more of the light, and therefore the brightness will only be affected by the angle between the surface and the light source. Now, some people will then show you a picture that looks like this. And by the way, if the person who made this picture is listening, I'm not saying that you didn't understand what happened. I'm just going to say that most people, when they see this picture, think the following, which is not true. Okay? What they think is that, depending upon the light source coming in, the more perpendicular it is, the more light you have reflecting out. That is true. But what's drawn here is that the amount of light coming out is the same in all directions. That is just not true, okay? And by the way, I want to thank Bertolt Horn, who, by the way, invented the shape from shading problems and most other computer vision problems way back in like the 70s and 80s, because I took my first computer vision course, and he made a big deal about this. And you see that, Bertolt? I was paying attention. What actually happens in Lambertian shading is the following, okay? When the light is reflected out, basically it falls off, so it's sort of equal area here. So you see that this amount, so more light is reflected perpendicularly out than is reflected sideways, okay? And in fact, as you fall off, this thing goes down by the cosine of the angle, so that actually almost no light at all goes out sideways. So a lot of light reflects back up, and almost no light at all reflects sideways. So you might ask, get ready, Megan, well, why does it look equally bright from all directions?
Well, why does it look equally bright from all directions?
I love it when stuff works. It's that same foreshortening effect, but this time it goes the other way around, right? If I've got sort of a pixel having a particular angle, so that's what this is meant to be, a pixel having an angle. When I look down through here, it has a smaller area, it's drawn sort of wrong here, than when I look this way. Think about it this way. If I had a camera out here, the same angle, right, would now get a much bigger area. coming into the same pixel. So if I understand the math right, and I think I do, what this means is that the amount of area that I see in the surface grows by the cosine of that angle, or I should say 1 over the cosine of that angle. So as that angle gets smaller and gets closer and closer to 90 degrees, right, I start to see an infinite amount of patch in the same little pixel. But over here, I'm putting out smaller and smaller and smaller light. And these cosines, in fact, here they are here, this one and that one, they cancel. And that's why it looks equally bright from every direction. So I think I got that right. I'm sure my computer vision colleagues are going to send me email or just make fun of me on the web if I got that wrong. But I'm pretty sure that's the way it works. What you need to know is that it appears equally bright from all directions. Here we're back to our diagram where we've got our incident light coming in, light going out in some direction, and the surface appears equally bright from all directions. That is, it is independent of your viewing direction. All right? So one way of thinking about this is that the BRDF of a Lambertian surface is simply a constant, and that constant is referred to as the albedo, and here it's just written as rho, and this is the rho sub d for diffuse. By the way, often when this is written, you'll see a cosine theta I in the denominator, and that's for compensating for this viewing condition, but I think that just makes life confusing. So we're just going to think of the BRDF as being a constant for a Lambertian surface. And so what that means is that the surface radiance is just going to be that constant times the source intensity, I, times the cosine of the incident angle, right? Because the irradiance is a function of the radiance of your source times the cosine of that angle, and then the thing looks equally bright from all directions. So that's usually written this way as just the magnitude of the source times the albedo, and you can write this as the dot product between the normal and the incident direction, right? It's just the dot product, the cosine, between the normal of the surface and the angle of the light coming in. And that's what's referred to as Lambertian shading. Here's an example of, again, a fake sphere, Lambertian shaded. And the idea, of course, is that, when it's pointing in the direction of the light source, it's brightest, and then it falls off by the cosine of that angle. Okay, so that's the matte component, the body component. What about the specular or the mirror component? Now, of course, in a real mirror, and you all learned this in high school physics, right? There's only a reflection at the perfect mirror angle. Remember, angle in equals angle out? I'm sure you learned that somewhere in your physics class. Well, so using our diagram again, what this says is that all the incident light is reflected only in a single direction. Okay? And I'm going to call that direction M for the mirror direction. And here we have V for the viewing direction. Okay? And so that light is only going to be visible when V equals M. All right? So I have to be so if I've got a point coming from right here, I'm going to see it right there at that point. And everywhere else, it's not reflecting over that. I might see it at a different point, but all the light is being reflected along a particular ray. All right? And so the BRDF is just what's called a double delta function. If I'm thinking about this on my surface, right, this angle down and the angle out has to be equal. But this is drawn difficult. It's in 2D. Not only do they have to be sort of at the same tilt, but they have to be in a plane, right? In other words, this and this have to be in the same plane. Because if I were to rotate it this way, all right, then it would now be bouncing off in another direction. And so that's why there's two angles. This is the tilt angle, and this is the rotation around angle that says basically one has to be pi opposite the other. So we take this BRDF and we stick it into our radiance equation, and what it says is that the radiance, essentially the brightness that we're going to see out, is the magnitude of the source intensity. The rho sub s is the specular reflection. So for example, it might be a darkened glass that filters out some light, so it still acts as a mirror but only reflects some percentage of it. That's what the rho would do. And then we have these two delta functions, okay? And These two delta functions say that basically the angle in terms of the tilt has to be the same, and also the rotation around have to be exactly pi different. That's what those two things say. Now remember, the delta function is a function that if the argument is 0, it's a 1, otherwise it's 0, and that's why it's written as a delta function.